So you are able to see the screen?
Yes, sir.
Okay, cool. So anyway, so last class, we have already started our the last topic of this course. Okay, that is a plastic analysis. Okay, so this we have already started, and I explained you a direct method, that is incremental method. How to do the plastic analysis, how to calculate the collapse load. That is the load at which the collapse happens. Okay, so this is what we told. So plastic analysis means a collapse means it is related to hinge only. Okay, so where the hinge is going to get formed. So this you have to find out, and the load which causes a sufficient number of plastic hinges to collapse a structure, that is our collapse load. Okay, so then that we are calling as a mechanism. The mechanism is what we call as the collapse. How many hinges or how this is going to collapse. Okay, and finally elastic plastic movements. We use these things, and then shape factor, load factor, say collapse load. This we are going to find out. Okay, so of course, for statically determinate structures, it is straightforward, because there is only one hinge only is required, right? But sufficient to collapse the structure. So it is very straightforward. You just find whatever you have done in the linear elastic analysis. That itself is straightforward applicable for statically determined. So you just find out the maximum bending moment, and then you relate it to MP, say, okay, not My, okay, the yield moment to MP, and then you solve, you will get the collapse load. So statically determinate, it is extremely easy and very straightforward. There is no difference, from plastic to elastic analysis. Only thing you have to replace bending with that plastic moment, you take it and you find out the collapse load. But when it is, and of course, this is the collapse mechanism, we are trying to say rigid link mechanism. Okay, in reality, it will not collapse like this. It will have a hinge and other things. It is not like breaking into two pieces. Infinite curvature is not possible, but this is how we assume to simplify our analysis. Now, for statically indeterminate structures, say, what we told was, this is also very straightforward only. So you have to do step by step. So initially you apply the load, say, okay, we don't know where the hinges are going to get formed. So you draw the bending one diagram, say. So from the bending one diagram, you can easily find out where is the place which has the maximum bending moment. Okay. So this, let us say for this problem, this was the place where you will have the maximum bending moment. So now what to do is you increase the load, say, such that, this whole thing gets plastified basically. Okay. So that load you store. Okay. Like this problem we said, 32 it was everything was fine, but when it comes to 40, yielding starts. When it is a 48, say, so obviously this reaches the plastic moment, so this, so the load is a 48, the kilonewtons. Now after the once this entire thing is plastified, say, what you have to do is, now this beam, the propped cantilever, becomes a simply supported beam. Okay, so this automatically comes into picture. So now the remaining load, or you can take the total load and then you can normalize also. So once again, you draw the bending one diagram, say, for this simply supported beam, and then once again you identify the point where you will have maximum bending moment, and then you keep on increasing the load, and finally at 54 kilonewtons. Say. So everything, this hinge also gets formed. This hinge also gets formed into our calculations. So when it is a statically indeterminate structure, say, what essentially you are doing is linear elastic analysis only, but the mechanism changes. So here it was a propped cantilever up to some load. Once a hinge has formed at some point, say, then it becomes something else. Now it has become like a simply supported beam for the remaining load, and then you can calculate the load factors and all other things from this, the expressions. Okay, so collapse load divided by working load, say. So this will give you the load factor. So 1.6875, which we have obtained for the previous problem. Now, in a similar fashion, say the same thing, only whatever we said. So you can do it, that way also, step by step also. Or if you want to generalize, say you want to write a computer program, so like a MATLAB program which can default, which can take everything into care, say. So this is very straightforward. Okay. So what we told was you take the same propped cantilever. So we write like alpha times P. So P is your working load. That is, in this problem, it was 10 kilonewton. Alpha is your multiplying factor, or the collapse or that load factor or whatever. So this is what we have to find out actually. Okay, so for this also, this problem, say, so now no need to worry about where hinge gets formed or whatever. So what you have to do is, so if you want to do it systematically, say, so what we said was you divide the analysis. So now these are the three, so now where hinges will get formed, so that you have to decide actually. So if you draw the, from your linear elastic analysis, you draw the bending moment diagrams here. That itself will tell you where the bending moments are maximum. So those points, there is a chance of plastic hinge getting formed. So like for propped cantilevers, bending moment will be maximum here, and then the bending moment will be maximum at below the load itself. So these are the two possible points. Anyway, here bending moment is already always zero at C itself. Okay, so this is not required. So there are 2 points of obtaining the plastic hinges. So now what we do is, you divide this beam into, say, two pieces kind of a thing. Okay, that is a one. So A to B is one area where you are having this one. Then B to C is another member, say. So you tabulate this one. So now you find out what are the bending moments. So that is due to the load, whatever is the bending moment, you just write, all these, this one. Then the residual plastic moment. So that is a 27, 27, 27, because you have to repeat statical indeterminate means you have to repeat the analysis. So in the starting, say MI is basically, okay. So this can be taken as zero, for stage one kind of analysis. And then you find out the load factor. That is this factor where one of the places, say, the things becomes plastic. So in this problem, we found out that A becomes plastic quickly. So 1 point is the load factor. So you multiply by 1.2 all these numbers, say, and then you get this the bending moments, the revised bending moments, which you have to do for your next step of the analysis. So now the bending moment initially was 22.5. After this load factor, it became 27. Now what B say 18.75 was the original thing. Now it has become 22.5 itself. Okay. So now this you have to start. So now the next step you have to do. So in the next step, what has happened was bending moment at this has become, propped cantilever has become like a simply supported beam. So here the bending moment is zero. So you apply the same load, say the 10 kilonewton. Now you find out, these B and the bending moments at all other places itself. So now here the residual moment is 4.5. Plastic is 27. So 22.5 was this what we have obtained here. So the remaining bending moment, say, is 4.5. So now you normalize this with respect to the applied bending moments. It turns out to be 0.15. So now you multiply, say. So you will get now these are the 27. So when you go for stage 3 analysis, say, now what happens is, so all the places bending moments are 0, 0 kind of thing. So when you do stage 3, say, okay, so that means A, B, you followed it. So here also bending moment is 0. Here also bending moment is 0. So there is nowhere, you have the lower, the beam cannot take the bending moments. Automatically, it collapses actually. Okay, so this is how, we try to do this methodology. Like you can write it in Excel sheet or whatever, or you can write a MATLAB program. See, like for example, if you have a fixed beam, say, okay, this is also indeterminate only. And let us say you have some, the load like this, okay. And now how do we start this problem? So now let us say you have some W load is given to you, some 10 kilonewtons, and MP is known to you. Now you have to solve by this problem, say. So what you have to do is, first thing is, now how many hinges are required here for this collapse? Fixed beam and some UDL, some, uniform distributed load is at some places, okay. And now how many hinges are required? So what is a statical indeterminate, this one for a fixed beam? So how many reactions, how many equations, and how many redundants are there here? So for fixed beams, how many reactions are there, So you have done in your analysis course, no? No. Quickly tell me for fixed, say, what is the indeterminate, say? See how many reactions are there? All of you are there? See how many reactions are there for fixed beam? At fixed support, say, how many unknowns will be there? Vani, tell me.
Three.
So indeterminate 3 are there at each support. So 3 plus 3, 6, and 3 equations here. So 6 minus 3 is 3 itself. Okay. So indeterminacy is, 3. So 3 is that. So now how many you followed, right? So this one happens here. So now to fail this, so we have these reactions, and of course the horizontal thing you can do. So now to fail this one, say. So now where are the possible locations of bending? The plastic hinges for this fixed beam. Yeah. See, where are the locations, the possible locations, for plastic hinges? See, if you draw the bending moment diagram, say for a fixed beam, so what are the possible locations of hinges? So like we have seen simply that propped cantilever say we have identified, right? So where the possible hinges are located. So now here also say, so where the possible, the hinges are located, the plastic hinges say, at the fixed support is one thing. Then maybe below the load say one more hinge is required. Then at this support say one more hinge is required actual. Okay, so three hinges are required to collapse this fixed beam. So if you want to draw this, spreadsheet kind of thing, so let us say this is A, and we don't know where these hinges are going to occur. So let us say this point is some B and this point is C, say, okay. So now you divide this into two pieces, that is AB and then BC kind of a thing. So now you make a table, okay. So that is a joint A, then B, and then C, okay. The stage one analysis. So in the stage one analysis, for this load, you find out the bending moments. Now you have the plastic movement actually. Let us say 27 kilonewton or whatever is a plastic movement set. So 27, this one. And finally, you have to divide by everything by divided by m naught. And then, you find out the load factors. So now among the load factors, whichever is the smallest, say, that is what you have to consider. And then you recalculate once again the bending moments. Okay, that's what we did. So here, 1.2, 1.44 or whatever. So this was the lowest load factor, 1.2 or whatever we have got. So this you take and you scale everything to 1.2. Okay. So now after this one, you the next step say. So the hinge has already formed at one point. So we don't know where hinge is going to happen, you see, at A or B or C. So automatically the code will tell you. Now in the stage two say, so you find out once again the bending moments, but the mechanism is different. So if it is a fixed beam say. So let us say, hinge has formed here say. So now then, this beam becomes like a propped cantilever. Okay. So this becomes, a propped cantilever kind of thing. So this is your stage two of the analysis. Now still it can take the load. Let us say hinge forms at this place, say. Now this propped cantilever becomes once again, a simply supported beam itself. Okay. So this comes. And once again, say the hinge has to form at another place for this beam to collapse. So you will be having stage one, stage two, stage three analysis. So once the hinges have been formed, say, it will lead to collapse. Okay. So this is like a straightforward procedure. If you are writing it on a computer, say, it is very easy to calculate these things itself. Okay. And now this problem, the portal frame, this is a very complicated problem. So now if you want to find out to see how it is going to collapse. So now, because the load is also acting at the joint, okay. So then, the possible locations of hinges are, so this one, then this place, then this thing, and then this one. Suppose if the load is like this, say, so the same problem. So let us say the load was, acting here in the middle. So now what are the possible locations of hinges? So load is not acting at the joint, it is acting here. So the possible locations of hinges are, anyway, this is one hinge is here, one hinge is here, then you can have a hinge here, then you can have hinge at any other place. It's a possible hinge formations where the hinge will form. Now load is acting here. So now what will happen? What is other possible location of the hinge when load is here, or when the load you are having a inclined here also there is a load, say. So now where hinges will get formed, what are the possible locations of hinges?
Below the load.
Below the load also. Here also there is a chance of plastic hinge actually. So here also there is a chance of plastic hinge. So you have to identify all these locations. So let us say here also say. So now you have 1, 2, 3, 4, 5, 6. So some possible locations are there. So you have to do the analysis. So anyway, so this problem say. So now you are having only this load is here. Okay. So you have to just only the load is acting at this one. So these are the possible locations of the hinges. Okay. And now the first step is you do linear elastic analysis. Okay, that's just to do a linear elastic analysis, and then you get the bending moments at all the places. Okay, so this is a joint one, two, like three members are there. Say. So this is one, then this is another member, and this is another column. Okay, so one, two, three. So now so this problem says, so you do linear elastic analysis, you find out the bending moment. So whatever you have studied in structure analysis, say. So this is also a indeterminate problem itself. So you have to do slope deflection or whatever methods, redundants and other things you have to remove, and then you have to get this the moments. So now you find out the bending moments. Okay, for the straightforward, just a simple linear elastic analysis. Now you tell me which is the most critical location where hinge will get formed. At what location? At 1, 2, or 3, or 4? Where hinge is going to, where bending moment is maximum? Yeah. So starting point. So where bending moment is maximum? Which joint, so 1 is here, 2 is here, 3 is here, 4 is here. So where movement is maximum? Tell me. So where bending moment is maximum at which joint? 1 or 2 or 3 or 4? See, this is our portal frame. Okay, so now from our linear elastic analysis for this load, okay, so you have calculated the bending moment. So bending moment at here is 27.21. Here it is a 21.75. Then it is 31 here, and here it is 59.62. Now you tell me which is a place where a plastic hinge will form. First plastic hinge, where it will, where the bending moment is maximum. Where bending moment is maximum. Tell me, just I have given the numbers also, right?
4.
4. So this is a place 59.62. So this is a where you will have a don't no need to worry about negative signs and other things. So this is a place the maximum bending moment is there for this problem. Okay, so maximum bending moment is here. So this is a place where first plastic hinge will get formed actual. Okay, so now anyway this is a residual plastic movement here, but this is an interesting problem here. The plastic movements for columns is 30 kilonewtons. It is different, for the entire thing it is different. And plastic movement for the beam is, 20 kilonewtons. Okay. So this is a difference. So 30, 30. So for beam, it will get plastified quickly rather than this one. So now you find out the load factor. So in the first stage analysis, your MIs are zeros actually. Okay. So this is 0. So now just to compute MP by M naught. So MP by M naught, if you try to compute, say that is 59. MP is 30 by 59.62. Okay, and 30 by 31, 20 by 21.75. So these are the load factors actually. Now among these load factors you have to take the lowest. So the lowest is 0.503 actual. Okay, and now you find out the cumulative movement. So that is MYs are 0. So this is all 0 for the starting case. So alpha into M naught. So this is 0.503 into 59.62. Okay, then the top one says, so this is 0.503 into 27.21. Okay, that is this one. Then this is a 0.503 into 21.75. Then 0.503 into 51.6 actual. So the load factor is constant. That is the lowest one you have taken. And these are the revised calculations. Okay. Now here the plastic movement is minus 30. Here also it has reached minus 30. So now this has become a plastic hinge actually. So and these are the residual, whatever the remaining things, which is under this thing. So now the plastic hinges formed the same. Now what you have to do? Now you have to go. Now still the frame is not going to collapse actually, because it will still support the load itself. Now the next step, so that is stage 2 analysis. So now once again, so the plastic hinges formed. So you have to solve this previous problem. Okay, so this is my one plastic hinge here, and this is fixed actually. Okay, now the same load is acting here. That is a 40 times alpha kilonewtons. Okay, so this is our thing. So now for this, once again, you draw the bending moment diagram. You followed. So the bending moment diagram you draw here itself, and then these are the bending moments actually. Now you find out the residual plastic moment, that is MP minus MI. So that means 65.09 in the minus 13.69 actually, which comes from the previous analysis. 65.09 minus 13 say 0.69 or whatever we have in the previous case. Now for this one, say 10.94 is there. So this also you substitute. So now 47 point 24 minus the 10 point that whatever we got previously, the 10.94, the previous movements. So now you subtract this one. So these are the residual movements actually. So now once you have the residual movements, say, so now you tell me where hinge is going to get formed, at which place the the plastic movement is very high, or at which place the bending moment is very high. No, don't see this first one. So this is only straightforward. This is for the total load actually, 40 times alpha. Now the remaining thing, if you see here, and now which is the most critical location. Now tell me where bending moment is high at 1, 2, 3, 4 is anyway plastic hinges formed actually. Now where it is high? So where it is high, you have to see this portion actually. So where the bending moment is high after subtracting the previous one. So where bending moment is, which joint? 1 or 2 or 3 or 4? Now, see this figure and tell me, straightforward. So where the bending moment is high?
2.
Uh, so where is it? 2 is, you are looking at this graph actual. Sorry, this one 19.06. Okay. What you told is correct actual. So why it is happening? Now, because the reason for this problem is 2 is becoming critical. The reason is, the plastic moments for beam is lower than the plastic moment for the columns actual. Okay. So this could be this one. So now, this 2, that is for stage 2 say. So 19.06. So 2 or 3. Sorry, which is the residual plastic moment where it is lowest. I'm sorry. Highest is 19.06. Okay. The residual moment where it is very small. No. See, the maximum is residual plastic moment is 1916, but where it is very small. Sorry, this you have to look at. Okay. So this one, if you try to look at here, so the higher this is almost 4.4. That is at the 3 place itself, and then you find out the load factors. You divide by this m naught. So these are the multiplying factors. Okay. And now which is the smallest one here? Which is the smallest here among these load factors? Just simply this divided by m naught, 4.4 by 52.61, 19.06 by 47.24. Say if you divide this by this, so you will get the load factor. Okay, so of course the residual plastic moment is 19. So still it has strength actually. It can take some more this one, but now this is joint 3 say it can take only 4.4 only. The smallest this one. So now what happens is, so this place it gets plastified very quickly. Okay. So now among these ones, the lowest load factor comes for 0.084. That means this 3 say it is going to get plastified very quickly actually. So now you take 0.085. So once again you find out the cumulative movement. So like you say 16.31 say plus 0.084 multiplied by 65.09. So this turns out to be 19.13. Now this one say this 14 point, this one will be my 19 point is 06 plus 0.084 into whatever the number you have say. So that if you multiply say this 60, sorry, not 19 19 point. So mi you have to take here. So the previous iteration say, and then you calculate this one. So you will get 14.81. So that this mi you have to take. That is a 10.94 actual. Okay, I think I'm sorry. So this is 13.69. So 13.69 say. So if you add this one, so you will get these are the numbers basically. Okay, the 14.89 will be like 10.94 say plus 10.94 plus this is 0.084 multiplied by 47.24. So this will be 14.89. So now after do this one, so this place automatically it becomes a 20, and the plastic movement it automatically happens in the column. So the 3 say the hinge gets formed itself. Okay, so this is our stage 2. Now although hinge has formed, still the it is this portal frame can take load itself, because 2 hinges only are there, because it's still fixed support say, still it can take the load actually. So still there are some joints which are not yet plastified. So now you go to the stage 3 of the analysis. Now the stage 3 of the analysis say, once again you have to do this problem: one hinge here, one hinge here, then this is a simply supported, this no, sorry, this is a fixed support. So now this is our load 40 times alpha. Okay, so once again you calculate the bending moments say. So all that straightforward is bending moments you calculate. Now you find out the residual plastic moment, that is mp minus mi. Mp is a 30, then for beams it is 20, for columns it is 30. So 30 minus mi. So this mi comes from this graph actual. Okay, so the 30 minus 19.13, so that turns out to be 10.87, 15.11. So you will get from the previous graphs itself. So these are the numbers. So once again you find out the load factors say. So alpha is equal to mp minus mi by m naught. You find out the lowest load factor is 0.073. So once again you repeat the procedure say. So now you will see 28.56, 20, 20, 20. That means joint 2 say this also has plastified actual. So first plastification here, second here, the last one is it's not the third one is at the joint 2 itself. So now still joint 1 is not plastified. So once again you do the analysis say, that is a stage 4 analysis or whatever, and then once again you repeat the procedure. So this also gets plastified actually. So finally all the things will get plastified. So 4 starts, this is the first plastic hinge forms here. second plastic hinge, third plastic hinge, and the fourth plastic hinge. So you have to do step by step analysis. And now the total load factor will be, you see, you have to add up all those things. In the last case, it is 0.0072 plus. Okay. The previous case was 0.073. Okay. Plus. Then, 0.084 plus. Okay. So this one will be the first one. Okay. That is a point, 503. That was the thing. Okay. So this is our load factors actually. So you add all those things, you will get the load factors at which things will get plastified. So this, of course, here the load factor will be 5 or maybe 0.6 or 0.7, because I think it has already, that 40 kilonewton is already, it has reached a stage, say, where plastification starts here. So this you followed it, you have to find out the load factor. So this is how you can do step by step, the analysis. So it is something like, if you draw the stress strain, movement versus curvature, say it is a linear up to some place. So the first plastic hinge forms, say. So then the whole portal frame has changed. Initially it was fixed. Now one side it is fixed. The fourth one plastic hinge forms. So after that, this is our analysis. Now once again, joint 3 plastic hinges formed. Then once again, this one other plastic hinge has formed. Then once again you follow, right, another plastic hinge gets formed, and then it goes like this actually. Okay, so this is how. So it is basically a linear elastic analysis only, but you have to do 4 times, or depending on your indeterminacy and other things to say. So each time you different the linear elastic analysis has to be carried out. So if you want to write a computer program or whatever, say, so first of all you identify where hinges are going to get formed. So suppose if the load is here, say, then maybe you may have to take this also. Instead of 1 2 3, say, you may have one, this is one member, 2 is here, 3 is here, then 4 is here, say. And then you have to write this joint also, and then you have to do step by step, and then you can, the whole things gets plastified. So this is a straightforward but cumbersome procedure, because you have to do so many stages and other things also. Okay, so this is how you can do. So the main observation what we said was, for determinate structures, it is very straightforward. It is the same as your elastic analysis, and your bending moment diagrams, it doesn't change at all. It just keeps on linear elastic like this. Okay, so Py Pu, and it's the same thing, very straightforward. Only one hinge is sufficient, so there is nothing to worry actually for determinate structures. But if it's indeterminate structures, so what is happening is your bending moment diagram changes. Okay, once one hinge is like a propped cantilever, or we have seen, once one hinge forms, say, it becomes a simply supported beam. The stiffness reduces. Okay, so you can see after one hinge is formed, say, that you will have a different thing. So different thing, and then after another hinge, say, another things will come into picture actually. So this is one very important observation, which you can make from our analysis. Okay. So now this method, say, whatever I showed you, the incremental method or something, it is you can write a computer program or whatever. But if you want to do by hand calculations or some manual methods, it becomes very tedious. But of course it is very rigorous. You will be understanding step by step all those important things also. So if you want to do a simple method, say simple, or a quick thing actually, and of course it can be applicable for simple problems. So then there are other methods, are the simple methods. So there are some theorems are there, which we will see: static method, kinematic method, those methods are there. So now for those methods, say, we have some conditions basically to be satisfied. So these are the conditions for elastic analysis, which already you people know from your mechanics of materials and structure analysis. Like you see, equilibrium has to be there. Then if it's indeterminate structures, so we also use compatibility actually. Okay, the compatibility, and then of course the simple bending formula. This is the formula on which the whole the analysis is based on. So these are the things for elastic analysis. Now, if you want to do plastic analysis, say, by a simple method, say, so these are the 3 conditions. One anyway is equilibrium. So the bending moment has to be a static equilibrium with whatever applied loads, the reactions. Then there has to be a mechanism for plastic analysis. Okay. So for plastic analysis, we are going to collapse. So there has to be sufficient number of plastic hinges, for the beam or a structure to form a mechanism. So this is the mechanism is more important in plastic analysis, because on the mechanism only we compute all our the analysis itself. And of course the plasticity, say, the bending moment in any section, say, it should be always less than MP itself. It should not cross MP. So these are the 3 conditions for the plastic analysis. The same thing only I'm writing here. So the conditions for plastic analysis, one is equilibrium. Okay, that is a bending moment diagram should be in equilibrium with our external loading. Then mechanism is very important, because on the basis of this only we are calculating all our analysis. Okay, so like where plastic hinges are going to perform, what type of mechanism it is going to be. So this is very important for us. And of course, the third condition say at no point in the structure will have a movement greater than the plastic movement actually. So these are the three conditions for plastic analysis. So based on these three conditions, so some theorems have been postulated, to develop simple methods. Okay. So one is what they call as, static theorem, or it is also known as, the lower bound theorem. So this theorem, what it says is, suppose if you have a load factor, say you have computed basis on the, on the basis of assumed bending moment distribution, which is in equilibrium with the applied loads. Okay, so that means, you have got the bending moment diagram from your equilibrium or from your linear, elastic analysis itself. And then what this theorem is says, and where the fully plastic moment of resistance is nowhere exceeded, say. So you are satisfying like these two conditions. So it is a equilibrium and then yield basically. So these two conditions, you are using here. So what it says is that if you obtain your plastic moment of resistance or MP by using the first condition and this one, so the load factor, say whatever you have obtained from this method is either equal to or less than the true collapse load factor. So this theorem, what it says is, if you satisfy among these three conditions, the first condition and then the second condition, say, then whatever load factor you get it, so it says that it will be the lower than the true collapse load factor. So this is what they call as lower bound or a static theorem. Okay, and of course people say this is a safe theorem also, because load factors will be either less or equal to the collapse load factor. Suggesting structure can carry a load, less than or equal to its actual load. Okay, so this is a safe theorem. So this theorem is based on two conditions. One is equilibrium and yield itself. Okay. So this is one methodology. Now the other one is upper bound or kinematic theorem. Say. So this theorem satisfies, it is goes on from the mechanism point of view. So if you find out a load factor, say on the basis of an assumed mechanism is either equal to or greater than the true load factor. Okay. So when several mechanisms are considered by assuming plastic hinge positions, the true collapse load, say, or load factor will be the smallest of these values itself. So this theorem, say, it is based on this condition. That is a mechanism kind of a condition, and of course equilibrium will be there. We will not be using this third point, say. So then based on these two, you do this theorem itself. Okay. So they say that, so this theorem will be, unsafe theorem or whatever load factors. There is a chance of getting high, the load factors from this kinematic theorem. And then another theorem is a uniqueness theorem, basically. So what this uniqueness theorem says is, if you find out a load factor, say, computed on the basis of bending moment distribution, which satisfies both plastic moment and mechanism conditions, is a true plastic collapse load factor. You followed? So, so it means, you have to satisfy all the conditions. So the equilibrium condition you have to use, mechanism condition you use, and the yield. So if you can satisfy all the things, and finally the resulting load factor corresponds to its value at rigid plastic collapse, and then this gives you the exact, the unique theorem. So if you can satisfy all the three conditions, say, so if you do equilibrium is satisfied, mechanism is satisfied, yield is also satisfied, then whatever load factor you will get it, so that will be a unique, the factor. That's what this theorem says. So the kinematic theorem, is the upper bound, static theorem is lower bound, and then both of them will converge if you satisfy all the three conditions itself. So static theorem is based on equilibrium, the kinematic theorem is based on mechanism criteria. Okay, so if we can find out, things, say, bending on diagram or the collapse moment, such that both of them are satisfied, so then you will get a unique, the load factor. That's what this theorem says. Okay, so now, so this what, so now these are the three theorems. Okay, so the criteria are these three: mechanism, equilibrium, yield, basically. So upper bound theorem, that is our kinematic theorem, say whatever it says greater than or equal to, this is our lower bound theorem, say. Unique theorem means it satisfies all the criteria, so then it will be lambda c itself. Okay, so that's what this theorem says. Now let us see here. So now if you want to use these theorems to find out the, the collapse load or whatever, so we make, the simple methods. For the manual methods, we make these assumptions. Okay, these assumptions are same as whatever I showed you in the last class for incremental method also, just to have a refresh. Okay, so what it says is the plastic movement, say capacity of a section is independent of the magnitude of applied bending moment. Okay, so MP is independent. It is like a a metal property or whatever, or that is a structural property or a cross section property or whatever. It doesn't depend on the applied bending moment. Then the plastic hinges, is said, these are assumed to form at points at which plastic rotations occur. Okay, and then the length of the plastic hinge is considered as zero. As already I told you in the last class, when there is a plastic hinge, say, it will be formed something like this. So these entire region, will get plastified. Length of the plastic hinge also we discussed. But when you do the analysis, we neglect all these things. Okay, so we say that plastic hinge will just form at this point itself. So length of the plastic hinge is considered as zero. And then the material is sufficiently ductile to undergo large rotations or changes in curvature at the constant movement without fracture, because ductility is very important for plastic analysis, because once a plastic hinge gets formed, say, if it is not ductile, say, although so that structure may collapse as a brittle fracture actually. So ductility is more important. Then of course axial load or shear force, said they don't change the value of MP, is also one very important assumption. Then the structure will remain stable until the formation of the last plastic hinge of failure mechanism, and serviceability would not be impaired till such time. So like for example, I showed you propped cantilever or portal frame, say, where one hinge is not sufficient, the structure is still stable until the last the plastic hinge, the failure comes, then only the structure is going to collapse. Okay, and then the loads acting on structures are considered to increase in proportion to each other. When there are two loads or three loads are there, so you have to increase them by a proportion, equal proportion of all these loads itself. And of course the continuity at each joint side, this also we maintain. So these are the assumptions actually. Of course these assumptions are valid for incremental method also. They are also valid for all the methods itself. Okay, so these are the most the important assumptions. So based on these assumptions, say, we try to, so these methods have come into picture. Now the mechanism, okay, already we have seen in our incremental method. So mechanism that that already we have defined itself. So mechanism, if you want to give a proper definition, say, it is something like the collapse of a statically determinate beam, say, is considered to be synonymous with the formation of plastic hinge. So statically determinate means one plastic hinge is sufficient, but if it is indeterminate, so more number of plastic hinges are required. And then the configuration of a beam, say, when uncontrolled deformation can occur, so that means the deflection becomes infinite, or curvature becomes infinite or whatever at constant loads, and finally collapse is called as a collapse mechanism. So mechanism means essentially it's a collapse itself. So if we take a simply supported beam, say, okay, so this is a bending one diagram. So how it is going to collapse, we have already seen. So at the place of maximum bending moment, say, you will see a plastic hinge here, that is one hinge is sufficient. So this is our mechanism actually. Okay, so this is a place where once hinge has formed, say, the deflection will be infinite or whatever, uncontrolled deflection happens. So this is a collapse mechanism for supported beam. So for a prompt cantilever, say, previously we have seen, so this is a bending one diagram. So the collapse mechanism will be one hinge formation here, one hinge formation here. So this is what we call as the collapse mechanism. So for fixed beam, say, you require three hinges. So first hinge, so this is a collapse mechanism, say, for a fixed beam itself. Okay, so this is what we call as a collapse mechanism. Now there are several other mechanisms are there when you look at portal frames and other structures itself. So there is what we call as a beam mechanism, then panel or sway mechanism, then gable mechanism. This is important for gable frames and others. Joint mechanism is possible. Then we can have a combined mechanism, that is a combination of one or two, like combination of beam versus and sway, or sway and joint, or you can combine all these things also. You can have a combined mechanism. So if you see this case, say, okay, so all the spans of a loaded beam, say, so if you see this case, so for a simply supported beam, say, now how many plastic hinges are required? So now what is the redundancy of a simply supported beam? See, what is the redundancy of a simply supported beam? See, all of you are there. So now how many plastic hinges are required? So all of you know, right? How many redundancies? For simply supported, it is 0, and the number of plastic hinges required is 1. Okay. Now, if it is a propped cantilever, say, so how many redundancy is 1, and the plastic hinges are required is 2 actually. Okay. Now, if you're having a fixed beam, say, and there is only the transverse load is acting, so redundancy is 2 basically. Okay. So if you are having this type of the load, only this type. So the horizontal reactions you can neglect at the supports. So you will be having two this one. So finally the redundancy is 2 it will be having here. Okay, so the number of plastic hinges required are 3: one hinge here, one hinge here, one hinge here. You followed? So this basically 3 hinges are required for collapse of this one. So you can see that the number of hinges for beam mechanisms is say. So if you try to write number of hinges, it is something like what is a redundancy plus 1. So this something like approximately you can say how many plastic hinges are required for collapse of this beam mechanisms. Okay. Now if it is a sway mechanism, say sway is something like this. It happens for these horizontal loads actually, essentially in portal frames. So this is what we call as a sway mechanism. Gable mechanism, say it happens only this type of inclined things are there, say this is how the gable mechanism. It is also like a sway, but it is something like you will have hinge here, hinge here. So this is also one type of typical kind of failure. Then we have a joint mechanism also. This means you have a joint here basically. So now the hinge gets formed and this connections say. Okay, so this happens when columns and beams are connected. See, like this is a 2-story this one. You can see the column, top column wall. So here this is, you are having a joint, and you can see the hinge has formed here, hinge has formed here, hinge has formed here. So this is what we call as a joint mechanism also. Okay, now the combined mechanism, say, so you can see this is a combined mechanism where you have a sway is also there, then beam is also there, beam mechanism, and then you are also having a joint mechanism also. It is a combination of all those the mechanisms. That's what we call as the combined mechanism also. This also the one typical type of failure actually. So that's what we said, the combined mechanism say. So like you are having 2-story this one. So you can see this is a joint mechanism, this portion is a beam mechanism, and this is also joint, and this is also beam kind of a thing. And then you are also having a sway also. So all the things are combined. So beam, then sway, then joint mechanism. So this also can happen actually. Okay, this is what we call as the combined mechanisms. So several type of failures are, or several type of collapses are possible here. So now what we have said was the number of plastic hinges is say for complete collapse, approximately you can say that if you know the redundancy say plus 1, you will find out the number of hinges. And how many number of independent mechanisms say. So we have, it is something like the number of plastic hinge locations actually. So where how many number of plastic hinge locations if we can find out, and the degree of redundancy say. So you can if you subtract, you will get how many number of the independent mechanisms also. Of course these formulas are not required, you see. By looking at the structure itself, we can decide how many number of plastic hinges or how many mechanisms we can easily calculate. Okay, this is, but this, if you want to have some type of a starting formula or some starting thing, you can use this expressions itself. So this so anyway, this is for a fixed this one. So now this is how the equilibrium method comes into picture. Okay, based on those assumptions. Yeah. So what this method is, it is very straightforward, very simple. So first thing, you have to draw the bending moment diagram, okay, of the structure, which you already know from your structure analysis course itself. So due to the applied loads, you just draw the bending moment diagram. If it is a statical indeterminate, say redundant, you remove, and then you can draw the diagram itself. Okay, so like for propped cantilever, say just now we have drawn for propped cantilever say. So this is my bending moment diagram. So this you have to find out. Now you have to identify the movement values at critical or potential plastic hinge locations are made equal to P. So now for this propped cantilever say. So we had, this is a point where you have maximum bending moments, you see. So these places you identify, and both of them are going to plastify. So when they are going to plastify, say initially the bending moment is 3 pl by 16, 5 pl by 32, or whatever we wrote those things. But when hinges get forms say, so here also movement will be equal to mp, here also movement will be equal to mp. So you have to equate both of them to mp itself actually. Now once you have equated, say now you find out the collapse load can be determined from the equilibrium equation. So now it is something like you have a bending moment diagram. The shape of the bending moment diagram you have taken from the linear elastic analysis, and these values you are not interested actually. And wherever bending moments are high, you have equated them to mp itself. So once you know mp these values say, now you go back, and then from the equilibrium say you find out the collapse load. Okay, so this is how we try to do this one. And of course the location of plastic hinges is obvious for beams, wherever below the concentrated load, you will have this one. And indeterminate beams also we have seen, it is usually you can find out actually. Okay, and there are so many loads are there, say you can calculate for all possible combinations also. And if there are so many combinations are there, so now you have to do for each combination what is the load, and you take the smallest value itself. Okay. And so now you will just show you like for example simply supported beam say. So this one if you see, okay, and now it's very straightforward. You just draw the bending moment diagram say. So this is a bending moment diagram for and just simply supported beam. Now where bending moment is maximum, so where the bending moment is maximum for simply supported beam subjected to UDL. See, all of you are there. So where bending moment is maximum? So only one is at one. Tell me
Center of
at the center. So what is the center value from the elastic analysis? WL square by 8 actually. So now what you have to do in the static method? So now this has to be equated to MP. You followed. So MP is equal to W into L square by 8, and then you automatically calculate say. So WU will be MP into this is our collapse. So sorry, this is a fixed beam. So for simply supported beams, so you equate it to this one. So now you find out. So WU is equal to 8 MP by L square actually. So statically determinate is very straightforward method. Now suppose if it is a fixed beam say. So now what is it? This is a bending moment diagram. Now tell me where bending moment. What are the possible locations of hinges from the bending moment diagram?
It supports and center of.
At the supports and of course the center point. Now to find out collapse loads, our static method what it says is at all these places actually. So you equate the bending moment to MP. So here also bending moment is MP. Here also bending moment is MP. Here also bending moment is MP. You have to equate to all of them to MP itself. So if you equate itself because of symmetry, so at this portion, this length is W into L square by 8, and this is MP. This is also MP. 2MP becomes actual. So 2MP is equal to W into L square by 8, and this is our plastic moment. So you can find out WU is equal to 16 MP by L square. Actually. Okay. For simply supported beam, it was 8 MP by L square, but collapse load for fixed beam is of course slightly higher. It is higher, almost double because of the fixed supports itself. Okay. So this is a very easy method to calculate, the collapse moments. So I will stop here. We will continue in our Monday classes, and then we will close this kinematic and both the methods. Okay. So if you have any questions, you can ask. So only one is there. I have stopped the